today I wish to partially cover the topic of embeddings. So some of my non-technical colleagues who are excited about the new possibilities which brings us ChatGPT from OpenAI, so they know how to work with them, how to interact, maybe even use some plugins, some prompting, so they are more experienced than me, but sometimes they meet some terms, some notions which are okay in the shadow of these generative pre-trained models. One such notion is embeddings. And today I wish to say something about the outline, about the history of this term, and why this seems misleading to almost everyone. This term occurred in mathematics, so we embed different mathematical objects like manifolds in topology, like graphs, like numbers, set of numbers in algebra. We have this notion in quite many mathematical fields. Perhaps the most common of them is topology. So imagine I have a two-dimensional surface. So everyone understands why this is two-dimensional, because, well, it has just a height and a width, just two parameters, and we can place it onto any other plane surface. We embed a sheet of paper. So the embedding is actually placing some object of some number of dimensions into a space of the same number of dimensions, or in the space of bigger number of dimensions. For example, if I transform this object into such a form, it is still two-dimensional, but it cannot fit the two-dimensional surface anymore. Instead, we can take a three-dimensional space and place it there. So I have just embedded this two-dimensional sheet of paper, which cannot fit two dimensions anymore, into a three-dimensional space. Well, there are pretty many such tricks in topology. So two-dimensional objects sometimes cannot fit even in three dimensions, so we have to use the four-dimensional space to do that. So this is something that we call embeddings in topology. But what is the relation of embeddings in topology and in other fields of mathematics to the embeddings which we use in our technologies connected with neural networks? But first of all, I wish to say something about how we represent data in computer science, in data science, in machine learning. Let us consider a very primitive example of what can happen to us in data science. So let us imagine that we collect some data about people, let's say children, and we are interested in just two parameters of them. So we draw a graph, and we are interested in the height and the age. And we take one person and put a point on the graph. And we expect something monotonously growing. Well, so we have collected some data and represented it on a graph, and thus have some picture like this. The bigger is the age, the bigger is the height. In data science and, well, in data analysis, we have a lot of techniques for reducing the dimensionality of data. Maybe the most primitive of them, the most simple, is linear regression, where we draw a straight line which approximates this data set. There are some better techniques. We can have a line which is more accurately describes the essence of this data. But anyway, if we analyze this data, we can figure out that it is mostly one-dimensional. So we can not ask about every parameter of a person. Well, we do not need to ask both parameters like age and height, we may ask just about an age. According to this general approximation, we can judge something about the height, and vice versa. Imagine that we have some information about our customers. We cannot ask each customer about everything in his life, about his habit, which is actually yet another dimension in this big data set, about his income, about his, preferences. We can learn only some not so many facts about your customers, but we want to know everything. So such models really help us in learning a lot of information given some small amount, because most of the information about each person is very redundant. So you learn just a couple of facts about a person, and then you can judge about many other facts about him or her. Well, in the language of data science, we can say that this somewhat one-dimensional data is an embedding, or is embedded into the whole two-dimensional space. So you know that there could be some outliers, like here or here, potentially, but we can just ignore them. So in data science, in data analysis, we usually just ignore the outliers and concentrate on the main trends. And the main trends tells us that we don't have to look outside this area, which is quasi one-dimensional. And we assume that everything else in these two dimensions is just empty. So this data set, one-dimensional data set, is embedded into the whole plane, two-dimensional plane. Now let us switch to the topic of NLP. NLP stands for Natural Language Processing. So we have many tasks and many problems which are connected to understanding natural texts by machines. Well, the key difficulty here is that our natural languages are very redundant. So we can express one idea with many different words by means of very different vocabularies, by using extensively synonyms, metaphors, and whatever else. Actually, the space of texts is much more bigger than the space of ideas. And we can say actually that the space of ideas is embeddable into the set of words. Moreover, if we consider not only the words and collocations and metaphors that we use in our regular speech or texts, we can note that potentially we could combine much more variants. Actually, most of our arbitrary combinations of words makes no sense. So we can say that the space of words and collocations and phrases from our regular texts is embeddable into yet bigger space of all combinations of words. So, and as a data scientist, we want somehow to process the natural language and reduce the dimensionality of texts. Perhaps the first very bright approach to this problem, which is word2vec. So let us limit with just English language. Well, how many words do you think there are in the English language? There could be different opinions about that. What is a word actually? What is an English word? One of the estimations is this number, 100,000 words. If you take a large corpus of English texts and remove some evident outliers, we can have approximately this number of words. In order to process a natural language, we wish to express any text as a set of numbers. Each of the 100,000 English words will serve as a separate dimension for us of this big vector. Let us consider an example of a sentence. Well, this sentence consists of 3 words. And what is the natural representation according to this approach? So we build a vector. It will be a very long vector of 100,000 numbers, most of them being zeros, just because the most of the words are not a part of this sentence. And in this long vector, we shall have exactly 3 ones. One of them stands for the word you, another for love, and another for cats. So this is the most simple approach. Well, if we have just one word, then we shall have a long vector, and then we can somehow compare 2 texts. If we have 2 texts, we represent both of them as vectors, and then find the distance between these 2 vectors. If they are close enough, then we can say that they consist of approximately the same words, and can conjecture that these 2 texts are about the same topic and express more or less similar ideas. But this quite primitive approach has certain drawbacks. For example, let us consider another sentence. I wrote it down, and it looks like cats love you. This sentence consists of the same words, so by this approach should be represented by exactly the same vector. But if we compare these 2 sentences, we see that they are more or less similar to each other in terms of the words being used, but they express somewhat different meaning. How do we solve this problem of similarity or dissimilarity between these 2 sentences? The second natural approach is to collect not only separate words, but write down also all 2 collocations. The 2 collocation is just a pair of words which are neighbors in some text. Cats love is a separate 2 collocation. Another 2 collocation is in this sentence is love you. So that if we want to vectorize this sentence, cats love you, by a more advanced approach, we shall have 5 ones in this long vector. So one stands for a separate word cats, another for separate words love, another word for separate word you, and besides we have 2 collocations. One is cats love and another is love you. You already noticed perhaps our first sentence also consists of 5 elements. 3 of them stand for separate 3 words, you, love, and cats, and besides it has 2 pairs of words, which is not similar to the pairs which we had in the upper sentence. So now we have 2 vectors which are quite close to each other, but slightly different. So they have 3 ones at the same position and 2 ones somewhere in some position which does not repeat across these 2 sentences. Then we have another problem. How many 2 collocations can we have in English language? So by the combinatorial rules, we have approximately this formula. 100,000 times 100,000. 10 to the power 10. So potentially we can have this many 2 collocations. This is quite a big number, but still we can process it with our computers. Might not be that fast, but still they are computable. If we want to increase capability of our NLP model, we should take a little bit bigger collocations. 3 collocations and 5 collocations maybe. Imagine if we take 4 of them, we have this huge dimensionality. and we cannot process it on our home PCs. Potentially we could work with this, but it will be really difficult for us. The solution of this problem comes from the sparsity of natural texts. Let us consider these two collocations. Chlorophyll tripod. This is a legal two collocation, but actually we never can meet these two words together in the natural English texts. So we performed a Google search for this, and well, Google reported that no one has used these two words together up to this moment. But of course, both of these words can have some other neighbors. So we quite often can see something like this, plastic tripod. If we have these two collocation plastic tripod, then there are quite a few options how to select the next word. One of the most probable is the word stand. Most probably after these two words, these two collocations will be followed by the word stand. So if we observe the whole set of three collocations that we can meet in English text, they will be less such three collocations than the theoretical number of 10 to the power 15. That's why we call the set of natural three collocations sparse. So if you take some random three words, most probably they won't build a collocation, a three collocation, which we can meet in corpora of English texts. So we have approximately 10 to the power 5 words in English language. And if we look through all the English texts and write down all two collocations from them, we shall have not the theoretical maximum, potential maximum of two collocations, but much less different collocations, which we use in real life. And if we switch to analyzing three collocations, well, theoretically there are possible this many 10 to the power 15 different three collocations, that is combination of three different words. Instead, in our real life, we see somewhat much smaller amount of three collocations. And the bigger the number of words in the collocation, the bigger chance that some random collocation of this size will make any sense. So the probability that we shall meet randomly constructed 4 or 5 collocation in English text will tend to 0. So again we have some comparatively low dimensional structure embedded into much bigger space of all theoretically possible collocations. This approach was implemented 10 years ago in the year 2013, and it is quite famous framework called Word2Vec. So they collected all accessible English texts and built an extensive statistics for all words and for all collocations up to a certain length. And actually this framework was the first very bright result in natural language processing. So as we know, in this approach, each separate word is represented by a long vector, consists of billion of numbers. Most of them are zeros, and exactly one of them will be 1. Let me consider a word king. So this will be some point in the multidimensional space. So sometimes we draw an arrow from the beginning of coordinates to the point which represents some object, so as to express that this is actually a vector. And let me also consider another word. This word will be woman. So the picture after we represent each word as a vector will look something like this. Let me also draw the third word, which will be man. We can take any two vectors and add them up. For example, now I wish to add up vector woman to a vector king. In order to do that, I must draw the same arrow like we have from woman, but starting from the point king. So we start from the point king as the beginning and draw just the same arrow as we have for woman with respect to the beginning of the coordinates. So we arrive somewhere here. And we also can subtract one vector from another. So now I want to subtract a vector man from this sum of two vectors. In order to do that, I have to start from this point and draw a similar arrow, but in the opposite direction. So we draw the arrow in the opposite direction, which is parallel and of the same length as this arrow, and we arrive somewhere here. So this is a point, also a vector, which stands for the sum of these two vectors, a king, a woman, and a minus man. And the magic of this approach, of this technique, is that if we consider yet another word, which is queen, it very surprisingly occurs to be very close to this sum. Well, initially this looked somewhat like magic to me, but okay, mathematically this is explainable by the means of the context. So if we observe the difference between the context where the word man is used and the context of word woman, so this difference will be very similar to the distance between the difference of the context of king and the context of queen. So these two blue dashed lines are parallel and almost parallel and almost equal in length. So if we have this collinearity, then we don't have to be surprised by learning that king plus woman minus man is approximately equal to queen. And by this technique, from this framework, even if we do not know the capitals of states, we can figure out just from this framework that, for example, relation of Riga to Latvia is approximately equal to the relation of Paris to France. In other words, we can say that if we treat this, all these words as vectors, then the vector which stands for Riga minus vector which stands for Latvia plus vector which stands for the word France approximately equals the vector which stands for the word Paris. Each vector which represents a word is naturally called also embedding, and this also stands for all collocations. So we can play not only with the words, but also with collocations. In this manner, we also can compare large texts, and we work with them as with vectors, and these vectors in Word2Vec are called embeddings. The same term, embeddings, is inherited from this framework and initially from mathematics, and now it is being used a special technology which is connected to neural networks. So let me say a couple of words about neural networks. I have drawn a very simple, very primitive example of what a neural network could look like. But for those of you who are familiar, I believe many of you are familiar with at least basics of neural networking. And this is how a typical recognizer could look like. So in a neural network, the data flow usually comes from the left to the right. As an input, a neural network receives signals, numbers. So there are 4 artificial neurons, so the computational model of a neuron. So these 4 neurons in the beginning receive the 4 numbers. These 4 numbers can represent anything. It could be a picture, it could be a text, it could be a set of words like we just have discussed. So we can feed a vector to a neural network, and this layer of artificial neurons transforms each number that they receive according to some very simple rule, and then transmit their outputs to the next layer of neurons. The strength of the signal represented by each arrow could be different, so we have different weights there. They could be even negative. Then the second layer transmit their outputs to the next layer of artificial neurons. In our case, this is the last output layer, and we treat it as an answer, as a result of a neural network. So if our task is to recognize something or distinguish between 2 subsets of a dataset, for example, if this number represents a picture where could be either a dog or a cat, then as the output we have 2 data from 2 artificial neurons. The upper neuron will stand for the probability of the image to be an image of a cat, and the lower artificial neuron then will produce the output which corresponds to the probability for an image to be an image of a dog. And then we compare which of the 2 values is bigger, and if the upper value is bigger, then we say, okay, our neural network decided that this image is an image of a cat. In mathematical terms, so we get an image as an input and produce 2 probabilities as an answer. So this is a transformation from one space to another, from a bigger space, multi-dimensional space, to a 2-dimensional space. I suggest considering a slightly more complex architecture for a neural network, which is known as encoder and decoder. So what happens in this neural network? So we start with feeding somewhat many numbers to the input layer, then the signals are transmitted to the next layer, to the middle layer, and here we have just 2 artificial neurons which contain encoded information about the input. And then they transmit their data to the next layer, and finally to the output layer, which is equal in size to the input layer. The architecture of this neural network is somewhat symmetric. So it started with a large number of the artificial neurons in the input layer. Then in the middle it has just 2 neurons or some small amount, and in the output it again has the same size as the input. We wanted to return approximately the same numbers. So what we had in the input, we expect to have in the output. There might not be exactly the same numbers as in the input, but we want them to be at least similar. And we take a big data set with a lot of photos or a lot of texts, and we encode it, feed a neural network with this input and make this neural network to produce very similar output on the given data set. And the first part of this neural network is called encoder. We take a large input and encode it or somewhat compress it into a smaller number of neurons. So in the middle of the process, instead of comparatively big input, we have comparatively small vector. So not much data can be stored in the middle of the process. And this is how we kind of forcefully reduce the dimensionality. So we take a multi-dimensional data and compress it to a lower dimensional space, to a lower dimensional vector. And then, if the encoder-decoder proceeds well, it runs the second part of the network and results in the output with somewhat very similar to what we had in the input. This means that we efficiently can store the input image or text or whatever in some small space, some small dimensional space, and then can effectively restore the initial result. So if this encoder-decoder works well, we can reduce the dimensionality. And this is what we actually want to do when we do data science, when we analyze data, because, well, we want to get rid of all the redundancies. We only want to get the essence of some data. And this small amount of artificial neurons in our neural network actually represents this essence of the input. So the number which we get in the middle of the process is called embedding. Well, this sounds a little bit misleading also for me, because these numbers are not the same as numbers here. So there is no visible connection between the vector here and the corresponding vector in the middle, as we could have in the spaces of words and collocations like we have in word2vec. The word embedding is inherited from the past, and now we use it also for the contents of the middle part of a neural network. You can wonder why do we need actually to make such transformation which does actually nothing with the input. Ideally we have the output which is equivalent to the input. So why this should make us happy? I will explain why we should be happy with these contents. After we have successfully built and trained such an encoder-decoder, we sometimes split it into halves. And both halves can be very useful to us. First part, well, starting from the input layer and ending with the middle layer, with the embedding layer, can help us to determine the similarity between two texts. So despite all possible differences in wordings, if the text or an image have more or less similar meaning, so these two embeddings also will be close to each other. And why the second part of the network is useful to us? This is used for generating something which is similar to the dataset on which this neural network, the whole neural network, was trained. For example, if it was trained on images, then we can do the following. We write down some random numbers, two random numbers, or, well, whatever neurons we have in this layer, and try to decode them into something. And if this encoder-decoder was efficient enough, this random data will be decoded in somewhat similar to the original dataset. Okay, if there was photos of cats then two random numbers here will result very similar to a cat in the output. If the network was trained on a set of documents, then assigning two small amount of random numbers in the middle layer will result in something that is very similar to a document. And this similarity has much more complex dimension than we had with our more primitive approaches like simple word-by-word vectorizing, or by using slightly more complex but not that complex word-to-vec, and we achieve much more impressive results here. I have composed two sentences to demonstrate the effectivity of neural networks. One is a sentence which a teacher can say to a student, "Your essay fails to address the main issue." And another, the red one, is somewhat that you could meet on the Stack Overflow. Well, something about programming. The issue arose when you failed to get the address of the function main. If we would use word-to-vec here or some similar approach, which is only word-oriented, we can follow that these two sentences are somewhat pretty similar to each other. Let us underline the equal words here. So I have marked the words which we can meet in both of the sentences. The word-wise intersection of these two sentences is very significant. Almost all words which you can find in the black sentence, you also can find in the red sentence. So we conjecture that they should be, in somewhat sense, very similar to each other. Also, we know that they can be used in very different contexts. But now I will write the third sentence. So this last green sentence seemingly is not that similar to any of the first two sentences, because it consists of all different words. So, okay, there is an article the, which is similar. We have many reasons to ignore articles at all, at least in word-to-vec. Well, if you read what is written in green color, you can feel that meaning of this green sentence is very close to the meaning of the black sentence, despite it uses all different words. Maybe there are synonyms, but nevertheless no intersection between these two sentences. As an experiment, I fed each of these three sentences to the neural network from OpenAI, which is specialized on building embeddings. So I got an embedding for each of the three sentences, and each embedding actually is a vector which has approximately 1000 dimensions. Again, I have only 2 dimensions on my paper. Okay, if we have an adequate projection from this 1000 dimensional space of embeddings to the 2-dimensional surface, we shall see picture which looks like this. So we have 3 vectors. More similar are texts. The closer should be the embedding vectors. And despite that black sentence and green sentence has somewhat empty word-wise intersection, they are very close in their real meanings. They mean the same thing. And in terms of the numbers, the distances between these pairs of vectors are approximately as follows. Well, the maximal distance is around 2. The distance between 2 random vectors is approximately 1, the expected distance. But despite these red and black sentences have word-wise intersections, the distance between their meanings, between the representations of them in the neural network, is quite quite big, and the distance between black and green vector is twice as small. So we can say in other terms that the green sentence is twice more similar to the black sentence than red sentence to the black sentence, so despite similarity in wording. This example shows that a neural network can catch the real meaning of these three sentences and compare not the sentences themselves, but compare their meanings. Imagine that you have read each of these sentences and somehow forgot the exact wordings and just remember the meaning of each of the sentences. And then you try to compare them not by word, but by their meanings. We can speculate that in fact you keep in mind not the wordings of the sentences, but instead their embeddings, or something that we could call an embedding or an analog of embedding of a neural network. I don't know how you can judge this exciting property of neural networks, the sentence not in the form of words, but in form of its meaning. I think that in our brains something very similar happens when we perceive and comprehend sentences and large texts and words. Just like us humans, neural network is already capable work not with concrete words, phrases and collocations, but instead with essential meanings, ideas which stand behind the words. And this seems pretty exciting to me.